Grab your virtual lab coats because today I'm putting on my battery engineer hat to investigate the absolute most common, yet most misunderstood, hidden cause behind countless electrical malfunctions. You know, whether you're dealing with a completely dead smartphone, a sluggish electric vehicle, or a car that just won't start, we are going to look right under the hood of battery chemistry to find the true culprit. So, why do batteries fail even when they hold a full charge? Have you ever had your phone just die when it still says 20%? Or maybe you've tested a car battery. The multimeter shows a perfectly healthy 12 volts, but the engine just clicks. No crank. Well, it's a super common mystery, and the answer? It doesn't lie in the voltage itself, but rather in a hidden saboteur living right inside the cell. Okay, let's dive into this highly structured seminar on the physics of battery health. We'll be covering the hidden battery saboteur, voltage equations in physics, chemistry, and temperature effects, diagnostic testing in BMS, identifying high resistance symptoms, and wrapping up with best practices for longevity. Section 1, the hidden battery saboteur. You see, countless batteries are tossed, and perfectly good systems are misdiagnosed every single day, just because people only look at voltage. But voltage is only half the story. The real villain here is internal resistance, or IR. Every battery has it. It is literally the physical opposition to current flowing inside the battery itself. Think of it as a hidden resistor connected directly in series with your battery's ideal power source. We measure this in milliohms. To give you some scale, a fresh, healthy lithium-ion cell sits somewhere between 50 and 150 milliohms. But as that cell degrades over time, that resistance can skyrocket to well over 1,000 milliohms. And as it does, it literally wastes your stored energy as internal heat. Section 2, voltage equations and physics. We really need to ground our diagnoses in the fundamental math of the electrical system here. And this brilliantly illustrates the exact physics of why this hidden resistance just crushes your battery's performance. Your terminal voltage under load, which is the actual usable voltage your device receives, is equal to the battery's open circuit voltage minus your current multiplied by your internal resistance. In simple terms, the more current your device pulls, and the higher that internal resistance is, the larger the resulting voltage drop. A battery practically never delivers its full theoretical voltage to your device when it's under a heavy load. Let's look at a genuinely shocking, real-world calculation. Imagine a standard 12-volt battery with just 0.05 ohms of internal resistance discharging at 100 amps. Super common for a starter motor, right? Well, that tiny bit of resistance creates a 5-volt drop. Your 12-volt battery is now instantly delivering only 7 volts to the system. Even worse, because power lost as heat equals current squared times resistance, you're instantly turning 500 watts of your electrical power directly into internal heat right inside the battery casing. In extreme cases, this is exactly what leads to warped plates, evaporated electrolyte, and thermal runaway. But internal resistance isn't just one single phenomenon. It is actually a combination of 3 physical sources. First up, ohmic resistance. This is the instantaneous physical resistance of the metal tabs, current collectors, and electrodes. Second, charge transfer resistance. This happens right at the border between the electrode and the liquid electrolyte, and it gets dramatically worse as a battery ages and that solid electrolyte interface, or SEI layer, builds up. Finally, diffusion or Warburg resistance. This is literally the speed limit of lithium ions physically moving through solid particles. This brings us to a really fundamental rule of battery design, known as Puchert's law. It basically states that as you discharge a battery faster, its effective capacity actually drops. But the energy isn't just disappearing into the ether, right? These Puchert law losses are physically driven by internal resistance. When you demand high power, that internal resistance diverts your precious energy into heat before it ever reaches your load. It is literally stealing your energy when you need high power the most. Section 3, chemistry and temperature effects. So we know the math, but how do different physical chemistries and environments handle this resistance buildup over many charge cycles? Well, not all batteries age the same way. Take lithium iron phosphate, or LiFePO. It has an incredibly low baseline resistance, sometimes under 5 milliohms, and stays amazingly stable over thousands of cycles. Compare that to the high energy density nickel manganese cobalt cells used in a lot of EVs. They start higher, around 20 to 80 milliohms, and their resistance grows way faster over time due to that dominant chemical layer buildup. And traditional lead acid, well, their resistance spikes pretty steeply as lead sulfate crystals physically coat the active plates. Now, what's really interesting about this slide is how temperature heavily manipulates the chemistry. In cold weather, especially below freezing, the liquid electrolyte actually thickens. Viscosity spikes, ion diffusion slows down, and internal resistance can increase by 3 to 10 times. It's a crippling effect. If you try to fast charge in this state, you run a severe risk of lithium pleading, which will permanently ruin the cell. On the flip side, hot temperatures temporarily lower resistance, making the battery feel super powerful. But it's a trap. That heat is silently accelerating SiI layer growth, electrolyte breakdown, and creating a permanent long-term internal resistance increase. Section 4. Diagnostic testing and BMS. Since we can't exactly crack open the battery to check on this degradation, how do we professional engineers actually detect and measure this hidden saboteur? We use 3 main testing methods. DCIR uses a direct current pulse to measure the immediate voltage drop. It's fast, and modern battery management systems rely super heavily on it to calculate a pack's state of health. Then there's ACIR, which shoots a 1 kHz AC signal. It's used by most handheld field testers. It's great for measuring pure ohmic resistance, but it misses the chemical aging part. Finally, EIS is the gold standard lab test. It sweeps across multiple frequencies to map every tiny flaw, though you definitely won't find that setup outside of a laboratory. Now, when we design large battery packs for EVs or grid storage, cell matching based on resistance is absolutely critical. In a series pack, the total resistance is the sum of all the cells. So just one mismatched, high-resistance cell acts as a bottleneck, imposing severe voltage sag on the entire string. It can destroy the whole pack's performance. In a parallel pack, it's inverse sum math. The cells with lower internal resistance end up doing all the heavy lifting, absorbing way more current than they were rated for, which creates incredibly dangerous thermal hotspots. Section 5. Identifying high-resistance symptoms. Okay, enough lab talk. Let's step back into the real world. How did this dense chemistry directly translate to the frustrating everyday symptoms you and I actually experience? Your smartphone dropping suddenly and shutting off at 20%? That's internal resistance causing the voltage to sag so heavily under load that your phone's undervoltage protection kicks in. An EV losing major range in the cold or taking forever at a DC fast charger? That's cold-induced resistance fighting the power flow. A power tool that bogs down or a starter motor that just rapidly chatters with a click but no crank? That is the sound of massive voltage drop stealing your power. To the user, total pack death usually feels totally out of the blue, but chemically, it's a progressive physical decline. In the early stages, as particle cracking starts, you might just notice a slightly slower engine crank or a minor loss of laptop runtime. By the mid-stage, as internal resistance effectively doubles, the device gets noticeably warm during use and voltage gets unstable. And by the late stage, the resistance is so severe that any heavy load causes an instantaneous voltage collapse, leading to a sudden, catastrophic power failure. Section 6. Best practices for longevity. So the crucial point is, how do we actually slow down this resistance growth? Well, I've got a step-by-step field guide with a few actionable everyday charging habits that will drastically minimize thermal and chemical stress. First, avoid pushing cells to extreme 0 or 100% states of charge. This limits the physical expansion and contraction that cracks particles over time. Second, thermal management is absolutely everything. Keep your packs in that optimal 15 to 35 degrees Celsius sweet spot. Third, if you drive an EV, always precondition the battery before fast charging in winter to prevent lithium bleeding. And finally, when you aren't in a rush, just use a slower charger to minimize mechanical stress and heat. All of this builds to our ultimate conclusion. The source material perfectly summarizes the entire thesis we've just covered with this incredibly powerful statement. A battery does not fail because it runs out of voltage. It fails because internal resistance rises beyond the system's ability to deliver current. It completely reframes how we need to think about system health, totally cementing that hidden resistor concept in our minds. I really want to leave you with a provocative thought here. The next time you're outside in the cold and your device unexpectedly shuts completely down with 20% left on the screen, take a moment to realize what just happened chemically. Your energy isn't gone. The hidden saboteur, internal resistance, just hijacked it. Treat your batteries right, keep them in their temperature sweet spot, and they'll keep delivering the power you need.